Hi Ashley, here's problem 35, and it's another opportunity to show how to do a derivative of a composite function step by step. So here it is, and rule number one, in case it wasn't obvious, is you always want to get rid of the radical sign. So I've rewritten it like this, and then we're going to use our we're going to fill in our let column and our then column, just like we've done before. So the simplest formula is pi x. So let p equal pi x, then dp dx equals pi. And then, again, following our step-by-step method to avoid getting confused at all, we rewrite the equation with our new substitution. And it's a little tedious to have to write everything over and over again, but this is the way to see what's happening and to make sure you don't get mixed up. So sine of tangent p to the 1/2. And so now we're going to let q equal tangent of p. And so, let's see, dq dp is secant squared p, and dp dx, we said earlier, was just pi. So, whoops, I don't need to write this again. Okay, so dq dp is secant squared p, and dp dx is just pi. So, again, remember the advantage of this method is that you can write everything in the form of multiplying ratios. So dq dp times dp dx, well, that's secant squared p times pi. But remember, we can cancel out the dp's, so we get what we want, which is dq over dx, and that's just going to be pi secant squared, but now we can substitute back in for p in terms of x, pi x. So now we know what dq dx is, and we'll use that later. Let me wall this off. So now what's our next substitution? We could do y equals cosine sine. We have sine of q to the 1/2. So our next substitution is going to be for sine q, because we know how to differentiate that. So what are we up to? Now we're at r. I have to squeeze this in a little bit, but that's okay. So sine r equals sine q, and dr dq equals cosine q. We know that. And we also know dq dx over here. So I'm going to skip a couple of steps, but you could write them out if you had to. But we know that dr dx is going to be this times this. So that'll come in handy in a minute. But anyway, let's keep going. So remember, we always, if we want to be careful, have to keep plugging things back in so we don't get messed up. So now we're at the cosine of r to the 1/2. Okay. So the next substitution is going to be let s equal r to the 1/2, and and ds dr equals 1/2 times r to the negative 1/2. So that'll come in handy because, well, you'll see. We'll do this all the way through. So now we have y equals cosine of s. Well, dy ds equals negative sine of s. And well, let's say we want to do y dy dx. That's what we want, right? So we know that that's going to be dy over ds times ds over dr times dr over dq times dq over dx. Going to wall this off. I'm just being redundant here, but just to emphasize, using these ratios, derivative ratios, makes it so easy to keep track of what you're doing. So the ds's cancel out, the drs cancel out, the dq's cancel out. So you're left with dy dx if you multiply those ratios together. So it's going to be negative sine s times, what did we say, ds dr, ds over dr. Well, that's 1/2 r to the negative 1/2 times dr dq, which is cosine q, excuse me, times dq dx, which is pi secant squared pi x. And so the last step would simply be to go back and substitute for s, of course, but we defined s here somewhere. Oh, here it is. Oh, well then you're going to have two r's, so you have to substitute in for this r and this r, but we've defined r, it's sine of q, and we've defined q, it's tangent of p, and we've defined p, it's pi of x. So it's extremely iterative is the word I was always looking for, or reiterative if you prefer. But you keep making substitutions, you're going to wind up with a very, very complex formula for the derivative, but that's what you have. That's what you get when you have to use the chain rule over and over again, as in this case. So I hope that's clear. As I say, the last part is just substituting in for these substitute variables, but that's just kind of rote mechanics. So let me know if you have any questions.